ẹ̀yin lẹ remove ẹ̀ bí.
ó dàbọ̀ tó fẹ́ duplicate ìkíní ẹ̀.
ẹni.
Ó fẹ́ copy ẹ̀ tó máa photocopy.
àṣìbó ti wà nù ìwé kọ́pì ìbẹ́ni kan tẹ̀ gba kọ́pì kan ni ìwé wa gba kọ́pì kan tán bá ó yẹ kán gba kọ́pì kan ni nà ìwọ́n tẹ̀ lè gba just one so kó wà ń bẹ̀ sódà kán máa dì sẹ́ wọ́n lè gba kọ́pì kan nà kán máa photocopy yẹn. ṣé mo lè start bẹ́ẹ̀ ṣá? Okay. Good afternoon, everyone. Good afternoon. Those of us that have not got a question, please raise up your hand so that we can know those of you that are yet to get a question. Okay. Copies will be made and everybody will get a copy. But instead of waiting for that to happen, I suggest we get started because our time has actually gone and we have to look at physics before we go. Okay, so let's get started. We're going to be looking at some questions as some of you already have it, and also the questions will also be projected so that you can also have another avenue of looking at the questions. And we are not just going to be solving the questions alone by telling you what the correct answer is. We're also going to be expanding the question to other areas that you guys also need to be aware of so that virtually all areas that needed to be covered will be covered, hopefully. So let's get started. The first one is on periodic properties of elements, specifically on ionization energy. And the question says, which of the following elements possesses the highest second ionization energy? What we know what ionization energy is the energy required to remove the valence electron from an atom in gaseous form to form a positive gaseous ion. And we have different types of ionizing energy. We have first ionizing energy, we have second, we have third, and so on and so forth. Now, the difference between the first ionization energy and the second is the number of electrons required. If you have an element in neutral state, let's say we have something like sodium, that's neutral. It has not lost any electron. The energy required to remove one electron from sodium so that sodium now forms Na+. That is the first ionization energy. But the energy required to remove another electron from sodium so that sodium now forms a divalent ion. That is the second ionization energy. That is the difference between the first ionization energy and the second ionization energy. So in this case, what's the matter? Okay. Sorry for that. So, like I was saying, the energy required to remove the first electron from a neutral atom in gaseous form to form a monovalent ion, that's the first ionization energy. The energy required to remove the second electron from that particular monovalent ion is called the second ionization energy. So, if you come across a question like this, there are two ways of going with this. Any element that wants to remove the first electron, then the electric configuration is going to be like that of a noble gas. That is the element that's going to have the second highest, is going to have the highest second ionization energy. What do I mean? If you look at the options here, let's start with magnesium. Magnesium has atomic number of 12. If you write it in form of the shell, what we have is 282. So if you remove the first electron from this magnesium is going to form 281. Does 281 has an octet structure or a stable electron configuration? It does not. So that's the point I'm trying to make. When you want to know which element is going to have the highest second ionization energy, all you need to do is remove the first electron from any element you are given. The atom or the element in which, having removed the first electron, the electron configuration becomes that of a noble gas, meaning that 8 electrons is now in the outermost shell. That is going to be the element that's going to have the highest second ionization energy. If you look at sodium, which is the correct answer, by the way, sodium is having atomic number of 11. The electron configuration in terms of shell is 281. Once we remove the first electron, what does it become? 28. And you can see now it has attained a noble gas electronic configuration. That is what you need. Or if you don't want to stress yourself at all, once you know the property of ionization energy in the periodic table, it is always the alkali metals that always have the highest second ionization energy. So if you are given a question like this within 2 seconds, you just need to ask yourself which one of them is an alkali metal. Because once again, alkali metals always have the second highest ionization energy. And if you look at option A, magnesium is an alkali earth metal. If you look at option C, is a metal, we call them the icocygens. Those are elements that in group 3. And then if you look at G, that is neon, that is noble gas. If you look at neon, by the way, so that you don't become confused, neon has an atomic number of 10. That's going to be 2A. Even though this is a stable electron configuration, when you remove one electron from it, what does it become? 27. That is no longer electronic configuration. So that is how you figure this out. So when you want to know which element is going to have this highest second ionizing energy, just remove the first electron from any atom you are given. Any atom that haven't removed the first electron, the electron configuration now becomes that of a noble gas, having 8 electrons in the outermost shell. That's going to be the one that's going to have the highest second ionization energy. So the correct answer for this is option B. And like I've said also, you can just save yourself the stress and just ask yourself which of the option is an example of an alkali metal. Only alkali metals or alkali metals always have the highest second ionization energy. And out of the 4 options here, the only alkali metal there is sodium. So let's come to number 2 question. Okay, number 2. Number 2 says, arrange the following in order of increasing atomic radius. We have 4 ions here. Calcium ion, chloride ion, potassium ion, and sulfide ion. And if you look at all the 4 of them very carefully, you will realize that all of them are isoelectronic ions. And what does that mean? They have equal number of electrons. They have the same number of electrons. Let's look at calcium ion. Calcium has atomic number of 20, and chloride ion, chloride has atomic number of 17. If you look at potassium ion, potassium has atomic number of 19, and finally sulfide ion, sulfur has atomic number of 16. If you look at the 4 of them, you will realize that all of them are isoelectronic. When we say isoelectronic in chemistry, it means they have equal number. Iso means equal number of electrons. How do we know? Here, this represents the number of protons in the atom. And don't forget, the number of protons in an atom is also called the atomic number. And without the charge here, we know that any atom in neutral state without a negative or positive charge always have equal number of electron and equal number of proton, meaning that originally, before this calcium loses the two electrons, it's having 20 electrons. But what is the meaning of the 2 plus here? It means it has lost 2 electrons. That's 20 minus 2, meaning this one is having 18 electrons. Not only that, before chlorine gain 1 electron here, is having atomic number of 17, meaning it's having 17 electrons and 17 protons. But this minus here means it has gained 1 electron, making 17 plus 1. That is equally 18. What about potassium? We know potassium, before it loses electron, has an atomic number of 17, meaning electron 17, proton 17. Because once again, when an atom is in neutral form, the number of proton and electron are the same. But the meaning of plus here means it has lost 1 electron. That's 19 minus 1. That is 18. And not only that, before this sulfur gains 2 electrons, it's having atomic number of 16, meaning that's 16 electrons. But the 2 minus here told us that it has gained 2 electrons. That is 16 plus 2. That is 18. So you understand what I mean by the 4 ion being isoelectronic ion. But that's not what the question is asking us. The question is expecting us to arrange them in increasing order of their atomic radius. What does that mean? We have to start with the one that has the smallest atomic radius, and then we end with the one that has the highest atomic radius. Since they have the same number of electrons, how do we figure out which one is the smallest and which one is the largest? Very simple. All you need to do is focus on these numbers. Don't forget, these numbers here are not number of electrons. All of them have 18 number of electrons. I've told you that already. What does the number here represent? Atomic number. What atomic number in chemistry? The number of proton. And that's the clue to it. Whenever you have isoelectronic ions, the higher the number of proton, the smaller the size. They are inversely proportional. So an ion that has higher number of proton will have smaller size, meaning that this calcium that has the highest number of proton, which is 20, we have the smallest size. So what do? That's Ca2 plus. The size will be less than what is second highest? If you look at this 20, this 17, this is 19, this is 16. So the next one is potassium. So potassium has the second highest number of protons. It's going to have the second smallest size. That's going to be K plus. So we've eliminated this. We've eliminated this. If you compare 17 and 16, obviously this one is higher than this. So that's the next one, less than chloride ion. And then finally, the sulfur, this one will have the highest or the largest atomic radius, that is S2 minus. So that is how it is done. Whenever you have isoelectronic ions, just focus on the number of protons present in it. The higher the number of protons, the smaller the size, and vice versa. Meaning that the ion that has the highest atomic number will have the smallest size. The ion that have the smallest atomic number, like sulfur, will have the largest size. So the correct one is going to be calcium ion less than potassium ion less than chloride ion less than sulfide ion. If you don't want to put it like this, all we have to do, if you want to arrange it in decreasing order, then we now have S2 minus greater than Cl minus greater than K plus and then greater than Ca2 plus. This is increasing order, this is decreasing order. But the question was asking us about increasing order, so which means the correct order is going to be this. And if you look at the options, that is option A. So it's as simple as that. And before I leave this particular question, we go to number 3. The next thing you should know about isoelectronic ion is the fact that if you have a polyatomic ions, isoelectronic ion, because there are certain ions that are isoelectronic or even isoelectronic species as a whole. When you have 2 or more species and they have the same number of electrons, they will also have the same shape. So when you have a particular, when you have 2 species and they have the same number of electrons, the shape is going to be exactly the same. Take for example, let's say you have something like carbon 2 oxide, that is CO, and then you think of a particular molecule that have the same number of electron as this. They will have the same shape. That's the point I'm trying to make. So let's say you have CO, and then you have something like nitrogen molecule here. Let's find out. Carbon. What are the number of carbon? How many electrons does it? How many protons does it have? Carbon, the atomic number is 6. What about oxygen? Atomic number? That's what? 8. And then everything now is going to be 14. Now, if you come to nitrogen, there are two nitrogen atoms here. One nitrogen atom has atomic number of what? 7. There are two nitrogen atoms here. That's 7 times 2, making what? 14. That's the point I'm trying to make. So these and these are also isoelectronic, even though they don't have charges on them. Because it's not only ions that can be isoelectronic. Neutral molecules like this, like carbon 2 or nitrogen, are also isoelectronic. So since this and this are having the same number of electron, they will have the same shape. As a matter of fact, we know from shape of molecule that any diatomic molecule is always linear. This is a linear molecule. N2 is also a linear molecule. So please take note of that. All isoelectronic species have the same shape. So let's come to number 3. The third question. So the third question is asking which molecule contains both dative, another name for dative is coordinate covalent bonding and a lone pair on the central atom. Now, two things are expected of the molecule here. Number one, it must possess a dative bond, and number two, it must also possess lone pair electron on the central atom. Meaning that for it to be the correct answer, it must satisfy those two conditions. If you look at option A, ammonium ion, does ammonium ion has dative bonding? Of course, it does. But does it have low pair electron on the central atom? It doesn't. I will show you in a bit. If we look at option B, boron trifluoride, does it possess dative bond? It doesn't. It possesses covalent, the normal covalent bond. And also, it doesn't have any lone pair electron. I'm going to show you in a bit as well. If you look at option G, which is methane, does it possess dative bond? It doesn't. It possesses the normal covalent bond. And does it have lone pair electron? It does not. The correct answer here is ozone. Now let me show you how to eliminate them one after the other. First things first, when you want to find out if a particular compound possesses lone pair electron, there are two ways of doing that. You can draw the Lewis structure. That takes time. That is, in jam, for example, you have probably 45 seconds to figure out the answer. So the best thing to do is use your time smartly. There's a simple formula that you can use to determine the number of lone pair electron on any atom. The formula is given as V minus B divided by 2. What does V represent? That's the number of valence electron of the central atom. What does B represent? That's the number of bond that is formed by that central atom and then divided by 2. Let's look at ammonium ion, NH4. If you want to draw the structure, it's like this, by the way. So you can see the central atom is nitrogen. And we know nitrogen belongs to group 5 in the periodic table. All elements in group 5 have 5 valence electrons. So our V is 5 minus how many bonds does it form? 1, 2, 3, 4. It forms 4 bonds here. Okay, so that is valence electron, that's 5. How many bonds does it form? That is 4. But remember, it is not just NH4, it is NH4 plus. What are the particular plus? What does it mean? It means it has, does it mean loss or gain of electron? It has lost 1 electron. So that's going to be minus 1. If it is negative ion, plus 1. If it's positive ion, minus 1. Then everything divided by 2. This is going to be 5 minus 1 minus 1 is minus 5 divided by 2. Of course, that's 0 divided by 2. And that's 0, meaning that the number of lone pair electron is 0. It doesn't have any lone pair electron. That's how you know. If you are looking at option B, boron, you do the same thing. Boron is like this. Fluorine, fluorine, and fluorine air. So this is boron trifluoride BF3. Now, boron is the first element in group 3, meaning that it has 3 valence electrons. That's 2 comma 3. So the number of valence electron is 3. That's 3 minus how many bonds does it form? This 1, this 2, this 3. That's minus 3 divided by 2. Once again, 3 minus 3 is 0. 0 divided by 2, that's also 0. It doesn't have any lone pair electron. Let's come to option B, CH4. By CH4, that is methane. All I have to do is just change this one to carbon. And this time around, carbon is the first element in group 4. It's at atomic number of 6, meaning that the valence electron is 4. If you substitute this particular formula, that becomes 4 minus how many bonds does it form? 1, 2, 3, 4. That's minus 4 divided by 2. Once again, 4 minus 4 is 0. 0 divided by 2, 0. Now, what about ozone? By the time we use the same formula, we see that ozone will have lone pair electron. So if we are talking about ozone, ozone is a special molecule because ozone forms both single and double bond. This ozone. That's the shape of ozone. That's what I was talking about earlier. That it forms both, it forms both double and single covalent bond. But in this case, when you want to calculate this, the central atom is oxygen. Oxygen belongs to group 6 in the periodic table. Is that atomic number of 8. So by the time you have V minus B all over 2. Now you have to be careful because look at this. This is a double bond, and this one is just ignore it for a moment. Take this one as a single bond. Take this one as a single bond. And then when you calculate the final answer, you just subtract extra bond that is present here. The number of valence electron, that's 6, minus how many bond? This one. Forget about this particular double bond. Take it as 1 bond. This is another one. Make it 2. Then divided it by 2. So we have 6. We have 6 minus this. That's 4. Then that's going to be 4 divided by 2. That's 2. But remember, the double bond that is here, you just subtract 1. I mean, that particular extra bond from this one. That becomes 2 minus 1. Then you have 1 lone pair electron. So you can see that out of the 4 options on the board, it's only ozone that exhibit not only coordinate covalent bond, but also possesses 1 lone pair electron on the central atom. And this formula works for any molecule at all. Either it is for ion or it is maybe for a neutral molecule. You can see we use for ammonium ion and we use for other neutral molecule like methane and also boron trifluoride. So that's for this. And before I leave this question, you must know the difference between dative bond and the normal covalent bond. In normal covalent bond, the electrons that are shared are equally contributed by the 2 or more participating atoms. Whereas in dative bond, only one of the participating atoms actually contribute the electrons that are shared. And there are several examples of compounds that possess dative bond. If you look at the board, ozone, exhibit or possess dative bond. Option A, ammonium ion, also possesses dative bond. Even carbon 2 oxide, carbon monoxide, CO, possesses dative bond. Ammonium chloride, NH4Cl, possesses dative bond. Another part, ammonium chloride is so unique that it possesses 3 out of the 4 types of bond that we have. Ammonium chloride, NH4Cl, has the normal covalent bond between nitrogen and hydrogen. It has ionic bond between the NH4 plus and the Cl minus. It also has the dative bond in the NH4 plus. Because there are questions in JAM that they can ask you which of the following types of bond is for present in ammonium chloride. Ammonium chloride has the three of them. It has ionic, also called a covalent bond. It has a normal covalent bond. It also has the dative bond. So let's take note of this. Let's come to number 4, the fourth question now. The fourth question. Okay, when chlorine gas reacts with hot concentrated NaOH, the oxidation states of chlorine in the products are, all we need to do here is, let's see what the products will be, and then we find out what the oxidation number of chlorine are in those compounds. But remember, this is reaction between chlorine and hot concentrated NaOH. So we have chlorine plus NaOH. This one is concentrated. It's going to give us NaCl plus NO3, then plus H2O. Let's look at this. So if you take a look at this, and you take a look at something like this, now, if this particular NaOH is no longer hot concentrated, if it's now cold dilute NaOH, there's going to be a slight difference in the products that we're going to get. This time around, we will still get NaCl. Instead of sodium triosochlorate 5, we are going to be getting sodium oxochlorate 1, then plus H2O. So that is why care must be taken for questions like this. You have to be sure of the concentration of the alkali. If it is hot concentrated, it should be sodium triosochlorate 5. If it is cold dilute, it will be sodium oxochlorate 1. So if you balance the two of them, we have 3 here, we have 6 here, 5 here, then we have 3 here. So if you look at this is one of the products. We have to look for the oxygen number of chlorine here. This is one of the products. We have to look for the oxygen number of chlorine. That's what the question is asking us. So what is the oxygen number of chlorine here? -1. And by the way, most of the time, you don't always need to calculate the oxidation number. All you have to remember is any neutral molecule. What should be the sum of the oxygen number? 0. You already know the oxygen number of sodium is always +1. So what can you add? What can you add to +1 to give you 0? We all know it's -1 instead of stressing ourselves and calculating. So that's why we know it is -1. The same thing, you can apply the same principle here. We know the oxidation number of chlorine here is going to be +1 every time. The number of oxygen is usually -2, with the exception of maybe it is peroxide, in which it's going to be -1, or maybe superoxide, in which it's going to be -half. So air is going to be -2. -2 times 3, that will give us -6. Now, if we add +1 and -6 together, we are going to get -5. What can we add to -5 to give us 0? That's +5. And by the way, if you don't want to do it like that, do it in the old-fashioned way by calculating your oxygen number of chlorine. Sodium is +1. Chlorine is what we need. Oxygen is -2. There are 3 oxygen atoms times 3. Everything comes to 0 because there's no charge on it. Then +1 plus Cl. This time this -6 is equal to 0. If you have +1 and -6 together, we get -5 plus is equal to 0. And then chlorine, if you take minus out the other side, it becomes +5. You don't always need to waste your time by doing that. Just ask yourself, which number can I add to whatever it is that you have gotten to give it 0? So the number of chlorine here is -1. The number of chlorine here is +5. So the answer is going to be -1 and +5. And if you take a look at the option, that is option B. So it's as simple as that. And by the way, before we leave this question, let me quickly explain something real quick. If I balance this to make it easy, so 2 here, everything else is balanced. Now, if you are careful here, you will notice something hot here, because this A verb, something strange about chlorine. Chlorine is always an oxidizing agent, isn't it? We know. Remember that chlorine leaches by what? By oxidation, isn't it? Now, which means that chlorine should be reduced since it's an oxidizing agent. An oxidizing agent is always reduced, whereas a reducing agent is always oxidized. And when something is reduced, amount to the oxidation number, it decreases, it reduces. So, and if you look at the number of chlorine here on the left hand side here is zero, because when an element is on its own, the oxidation number is always zero. And you expect that the oxidation number of chlorine on the right hand side is supposed to be negative because it should reduce. It reduces to form -1 here. But what happens? It increases to form +5 here, meaning that the oxidation number of chlorine does two things. It reduces, which means that it became reduced, and it also increases, meaning that it became oxidized. So you have a single element that is undergoing simultaneously oxidation and reduction at the same time. In chemistry, we refer to such a reaction as a disproportionation reaction, or you call it auto-oxidation reaction. Once again, a reaction in which a particular element undergoes simultaneous oxidation and reduction is called disproportionation reaction. Disproportionation reaction, it is also called auto-oxidation reaction. So that's the name of the process whereby a particular element undergoes simultaneously oxidation and reduction. This proportionation, because they can ask you, they can give you some, I think I've seen questions where equations like that are given, and then you are asked that which of the following reactions is an auto-oxidation reaction. Simply put, which of the following reaction is a reaction in which a single element is undergoing simultaneous oxidation and reduction? Either we call it this, or we simply call it auto-oxidation reaction. So that's for that. Let's come to number 5. Number 5 says, according to Arrhenius collision theory, the rate of reaction increases with temperature, primarily because the question is asking us, why does increase in temperature, why does it lead to increase in the rate of the reaction? Now we know that there are 7 major factors that affect the rate of reaction, and temperature is one of them. We know that whenever we increase temperature of a particular reaction, the rate of the reaction increases. But the question is why? What does increase temperature? What does it do? Primarily to increase, primarily means mainly to increase the rate of a reaction. Now, it does two things, but that is why the question says primarily. When you increase the temperature of a reaction, the first thing it does is it increases the energy of those molecules of the reactant, kinetic energy. And you know, the molecules of the reactant will now be able to move faster, they collide with one another more, and that gives rise to what we refer to as effective collision. Because the higher the number of collision, the higher the number of effective collision. And if you don't know what effective collision is, effective collision are those collisions that lead to the formation of a product. Because not all collisions will lead to product formation. There can be 1,000 collisions, and out of that 1,000 collisions, only 300 might lead to the formation of a product. Then we call those 300 that lead to the formation of a product effective collisions, and the remaining 700 that did not lead to product formation ineffective collision. So when temperature is increased, the first thing that happens is the molecule become energetic because they gain energy in form of kinetic energy, become more energetic, and since they become more energetic, they will begin to be able to collide more. So the number of collision now increases, but that isn't the answer, even though the option is there. What majorly makes that particular chemical reaction to increase due to increase in temperature is the fact that when temperature is increased, the molecules are able to absorb energy in form of heat, And that particular energy they absorb will make majority of them, a substantial number of them, to be able to have energy that is either equal to or greater than the activation energy. Don't forget, the minimum amount of energy required for a chemical reaction to occur, that's what they refer to as activation energy. And you know that the energy possessed by molecules of reactant, if it is less than activation energy, no reaction occurs. For a reaction to occur, one of two things must happen. It is either the energy possessed by the molecule is exactly equal to the activation energy, or the energy possessed by the molecule is greater than the activation energy. So essentially, when you increase the temperature, what we are trying to do is we are giving enough energy to majority of the molecules so that the energy possessed by them will at least be equal to or greater than the activation energy. So if you take a look at the option, so option A, the activation energy decreases, we know that is wrong. All right, because the only thing that reduces the activation energy of a reaction is what? Is a positive catalyst. That is how catalyst increases the rate of a reaction, by reducing or by lowering the activation energy. Temperature doesn't do that. Temperature has no effect whatsoever on the activation energy. Only catalyst does. And catalyst is the one that reduces the activation energy. We look at option B, the frequency of collision increases. It's true, but that is not the major, that's not the primary reason why temperature increases the rate of reaction. The major one is option C, a larger fraction, a larger number of molecules possesses energy greater than the activation energy. Now, the question can be structured in another way, in such a way that the answer will now be option B. Let's go back to that particular option B once again. So the option B is, let's go back to option B. So the option B is saying that the frequency of collision increases. Question that I usually ask in JAM, in which the answer B is going to be correct answer here, is the effect of concentration. They can ask you that why does increase in concentration of reactant lead to an increase in the rate of a chemical reaction? That's why. Because when you increase the concentration of reactant, that will increase the number of collisions or the number of effective collisions. They can also turn it around. They can ask you, why does decrease in concentration of reactant, why does it lead to a decrease in the rate of reaction? When you increase the concentration of reactant, it increases the rate of reaction by increasing the number of effective collisions. The reverse is going to happen. If you now reduce the concentration, that will also lead to a decrease in the number of collisions. So increase in concentration will lead to increase in the rate of chemical reaction by increasing the number or the rate of effective collision, the number of effective collision, whereas a decrease in concentration will also lead to a corresponding decrease in the rate of chemical reaction, because it's going to lead to a decrease or a reduction in the number of collisions. Let's come to number 5 now. So number 6. So which of the following processes result in a negative entropy change? And those places where you see question mark, they are supposed to be arrow there, pointing from the reactant to the product. So if you look at option A, CaCO3 to give CaO plus CO2. As a matter of fact, read the options. If I know about entropy change, what is entropy? Entropy is defined as the measure of the degree of disorderliness or randomness of a chemical reaction. In simple English, it simply means that the measurement of how chaotic or how orderly the molecules of a particular system is. Take a look at solid. In any solid molecule, the particles are in a fixed position because they are held together by strong intermolecular force of attraction. They are unable to move from one place to the other. They don't have translational motion, meaning that they can move from point A to point B. They are in a fixed position. We say that they vibrate about their main position. But if you look at liquid, the molecules of liquid are able to move from one place to the other, even though it's a short distance, because there is force of attraction holding them. But if you look at gases, Even under kinetic theory of gases, one of the postulates of kinetic theory of gases is that the force of attraction between molecules of gases are what? Are negligible. What does that mean? It's as if they are non-existent. And because no force seems to be holding them together, the molecules are able to travel and move about. That's why they can move in various directions. We call it zigzag or Brownian motion. What does that mean? It means that solid have the lowest entropy, liquid have the second lowest entropy, gases have the highest entropy. Meaning that entropy increases from solid to liquid and then from liquid to gas. So anything that will lead to changing something from solid to liquid, that's positive entropy. From liquid to gas, that's positive entropy. But anything that will change a gas to liquid, that's negative entropy. Anything that's going to change a liquid to a solid, that is also negative entropy. What am I trying to say? Let's look at melting. What happens during melting? A solid changes to liquid. That's positive entropy. What about evaporation? What happens to evaporation? A liquid changes to gas. That's a positive entropy. But what about the opposite of that? What about condensation? What is condensation? A gas now changes to liquid. That is negative entropy. Isn't it? So the same thing with freezing. What happens during freezing? A liquid changes to solid. So whenever there is change of state from solid to liquid, that's positive entropy. From liquid to gas, that's positive entropy. But if reverse is the case, then that is negative entropy. When a liquid freezes and changes to solid, that is negative entropy. When a gas condenses and changes to liquid, that is also negative entropy. And if you look at the board, let's go back. Okay. Okay, so now if you look at option A here, you can see on the left hand side, you have solid. And then, if you look at the right hand side, there is CO2, gas. So from solid to gas, that's positive entropy. If you look at option B, which is the correct answer, on the left hand side, you have gas. That's water in gaseous like steam. On the right hand side, what do you have? You have liquid. That is condensation. That is negative entropy. If you take a look at option C, let's come to option C. So you have, let's look at option C. Then okay, so if you look at option C, you have solid on the left hand side, and then you now have aqueous and aqueous. What's aqueous? That's in liquid form. So it's like something that is melting because melting will change from solid to liquid. That's also positive entropy. And copper, sheko, any- oh, no, no, that's okay. The size is the size is okay like that. The size is okay like that. So let's go to 6 then. No problem. No, no, the size is fine like that. The size is okay like that. Okay, so yeah, size in our okay. That is okay. Yeah, it's fine. The size is okay like that. That's in our okay. All right, sorry for that. So I was telling you that if I'm talking about increase in entropy, something must be changing from either solid to liquid or from liquid to gas, or maybe from even solid to gas. Or don't we have sublimation? After all, we have material that can sublimate, that can change directly from the solid state to the gaseous, maybe like iodine, something like ammonium chloride, something like dry ice. For example, dry ice is talking about solid CO2 and so on and so forth. But anything that involves condensation, that is from gas to liquid, that is negative entropy. Not only that, you can also calculate and find out if a particular reaction is having positive or negative entropy from the balanced equation. Let's take a look at this particular option D. And like I told you, the question mark here is actually supposed to be an arrow pointing from the reactant to the product. Let's look at let's look at it here. So here we are having 2NH3 to give us N2 and then 3H2 gas. And by the way, when you have a reaction like this and you want to calculate your change in entropy, it's always change in entropy is equal to the entropy of the gaseous product minus the entropy of the gaseous reactant. How does this work? All you have to do, and by the way, when you're calculating change in entropy, your only focus is on gaseous substances. You don't deal with aqueous substances, you don't deal with liquid substances, you do not care about solid substances. If you look at the right answer, these are the products. This 1 mole of nitrogen gas, 3 mole of hydrogen gas. So that's 1 plus 3, giving us 4 minus this is the only reactant here, 2 moles of ammonia gas. That's going to be 2. That's going to be plus 2. So you can see is a positive entropy change. The only reaction here that leads to a negative entropy change is option B. And you don't even need to stress yourself. You can see gas is on the left hand side and then liquid is on the right hand side. Meaning that it is changing from gas to liquid. That is condensation. Once again, let me repeat. Any reaction that involves melting, maybe of ice, something is changing from solid to liquid, that's positive entropy. Any reaction that involves sublimation, changing from solid to gas, that's positive entropy. Any reaction that involves evaporation, for example, or boiling of water, after all, when water is boiled, what happens to it? It's changing from solid, from liquid to gaseous state. Boiling and evaporation, they are also examples of positive entropy changes. Mixing of gases is another example of positive entropy change. When you mix 2 or more gases, their entropy, the rate of disorder increases. So these are 4 things that I told you. Now, what about the opposite, which is negative entropy change? Number 1 is freezing or solidification. When something freezes, it's changing from liquid to solid, like freezing of water. When you are talking about condensation, that is another example of a reaction involving negative entropy change. Condensation is when something changes from gas to liquid. Not only that, we're talking about deposition. Deposition is the opposite of sublimation. That's when changing from gas directly to solid. That is another example. Number 4 is liquefaction of gases. Liquefaction, don't forget, when you want to liquefy gas, what do? You reduce the temperature, you increase the pressure, all right? And then number 5 is compression of gases. When you compress gases, you are changing them from gaseous state into liquid state. Look at our various houses. If your gas cylinder, the gas cylinder that are using in the house, become exhausted, we take them out to where we want to fill them. And then they compress that particular gas into the cylinder. That's why if you hold the cylinder and you shake it, it's as if there is liquid or water in it. So compression of gases is another example of negative entropy change. So you must know the positive example and the negative example. So I believe that is understood. Let's come to number 7 now. Number 7 says, in a setup where two cells are connected in series, cell 1 deposits 0.635 gram of copper, and then cell 2 evolves a gas. If the second Okay, if the second cell contains dilute H2SO4, what volume of oxygen is involved as STP? This is an example of Faraday's second law of electrolysis. If you remember, there are two ways of defining it. We know that Faraday's first law of electrolysis tells us that the amount or the mass of an element deposited or discharged during electrolysis is directly proportional to the quantity of electricity passed. That's the first law. Faraday's second law, on which this question is based, tells us that when two or more, or maybe to put it in proper perspective, when the same quantity of electricity is passed through different electrolytes connected in series, the number of moles of the element discharged or deposited is inversely proportional to the charges on them. Or you can define it another way by saying that Faraday's second law of electricity states that when the same number of or the same quantity of electricity is passed through different electrolytes, the mass of the element discharged or deposited is directly proportional to their electrochemical equivalent. So these are the two ways of defining it. So we have two cells here. In one of these cells, copper was deposited. In the second cell, cell 2, oxygen is given off. And our job is to find the volume of oxygen that is given off at STP. We can approach this in two ways. We can use the formula method and we can use the other method. For example, let's start with copper. We know copper is divalent Cu2 plus. It will gain 2 electrons to become deposited as copper. And the 2E here means that it is 2 Faradays of electricity that is used. Meaning that 2 Faradays of electricity deposited 1 mole of copper. What that means is 2F, that's 2 Faradays, now deposit 1 mole of copper. And we know 1 mole of the copper has a mass of what? 63.5. 1 mole of any metal is the molar mass. That's the mean. 1 mole of sodium is 23 grams. 1 mole of magnesium is 24 grams, and so on and so forth. So 1 mole of copper is 63.5 grams. At times, they approximate it to be 64 grams. Then we are now asking ourselves, how many moles of electricity we now deposit? We have been told that 0.635 gram was deposited. All we need to do now is cross multiply. If you cross multiply, this becomes x times 63.5 is equal to this times this become 2f times 0.635. If you make x your formula, x now becomes 2f times 0.635 divided by 63.5. And Don't forget, every 10 air is in coulomb because that is the unit of charge. And by the time we do the calculation here, let's find out what will it give us? What? 0.02. So that's 0.2 farads. Meaning that the quantity of electricity required to deposit 0.635 gram of copper is 0.02 farads. And don't forget what the law says. When the same quantity of electricity pass through different electrolytes, it means that this same 0.02 Faraday that deposited 0.635 gram of copper will also liberate the oxygen gas we are looking for. All we need to do is now find out where will the oxygen come from. Oxygen always come from what? From water, isn't it? And all we need to do is write the balance equation for that. H2O will give us H2 plus, or you can, to make it simple for you, you can just write your ionic equation straight away. So O2 minus, because we know that oxygen is a divalent ion. O2 minus to give us oxygen gas, and then electron. Why is the electron on the left hand, on the right hand side here, and electron is on the left hand side here? Because we know that this copper is a metal, and metal is always reduced, and reduction always occurs at the cathode. That is why you have the electron here. We know the type of reaction that occurs at the anode is oxidation, and oxidation is loss of electron. That is why we have the electron on the right side here. So now there are two oxygen atoms. So we have to balance. That's why oxygen here. The next thing we have to do now is balance the charge. Here you have 2, that's minus 2. That's minus 4, meaning that the charge on the left hand side also has to be 4. That's 4, that's minus 1. So everything is balanced now. And remember here, 2E is equal to 2 Faraday. 4E now is equal to 4 Faradays. And then we are almost there. All we have to do now is know that 4 Faradays of electricity actually liberate how many mole of oxygen at SCP? 1. And we know that 1 mole of a gas at SCP occupies a volume of 22.4 dN3. So that 4 Faradays liberate 1 mole of oxygen, and 1 mole of oxygen at SCP occupies a volume of 22.4 dN3. Then we now find out how many volume of oxygen will 0.02 Faraday now evolve. So 0.02 F will now liberate or evolve how many dN3 of oxygen. So because on the multiply as usual, so here we now have X times 4F is equal to this times this, 0.02 F times 22.4 dN3. And if you divide both sides by 4F, so our X now will be F, will have cancelled F. And then we now have 0.02 times 22.4 divided by 4. What would that give us? 0. What? 112 dN cube of oxygen. But if you look at the option, the answer are not left in dN cube. The answer are left in centimeter cube. But we know that 1 dN cube is equivalent to how many centimeter cube? 1000. Meaning that 0.0112 dN cube is the same thing as 0.112 times 1000 centimeter cube. By the time we are done multiplying the 0.112 by 1000, what are we left with? Option A, that is going to be 112 centimeter cube. So that is how to tackle this. Now, like as some of you are writing, do that. Then there is another method of doing this that I want us to explore, so that you can have two ways of doing it, and whichever one you think that is better for you, or you understand better, or you think it's faster, then you can adopt them if and when you come across questions like this. Let's do that quickly. Okay, let me show you another way of doing this. Remember the last time when I was defining Faraday's second law of electrolysis, I told it can be defined as when the same quantity of electricity pass through different electrolytes, the number of moles of the element discharged or deposited is inversely proportional to the charges on them. I can write that mathematically like this. Number of moles, N, is inversely proportional to the charge on them. The charge on them is C, meaning that we can now say N is equal to, if we replace this proportionality sign with equality sign, we introduce a constant K. And if a constant apply, then we now have K is equal to NC. So we can expand this one and say N1, C1 is equal to N2, C2. This is where I'm going. So when you see a question like this, even if it is up to 3, if they give you 3 cells, that's going to be N1, C1 is equal to N2, C2 is equal to N3, C3. Then you just break them into 2. We have copper in one, we have oxygen in the other. Then you can now say this one is N oxygen, C oxygen is equal to N copper, then C copper. NO, meaning the number of moles of oxygen. CO, that's the charge, that's the number of electricity required by oxygen. NC, that's the number of moles of copper. And CC, that's the charge or the number of electricity required by copper. Now, don't forget mole. N is equal to mole, and we know that mole is mass all over molar mass. That is for a metal. But if you want to calculate the number of mole of a gas, how do you calculate the number of mole of a gas? That's the volume of the gas divided by what? 22.4 dm³. For example, if I add something like 1 point, if I have maybe something like 2.24 dm³ of oxygen, if I want to calculate the number of mole of oxygen in 2.24 dm³ of oxygen, all I have to do is say number of mole is equal to this, the volume 2.24 divided by the volume of the gas at STP, which is 22.4. My point is this: when you want to calculate the volume of a gas at STP, you divide the volume of that particular gas by 22.4 dm³. If you want to calculate the number of mole of any metal, you divide the mass of the metal by the molar mass. And the number of mole of oxygen is the volume of oxygen. That's what we have to calculate all over 22.4 dm³ times the charge on oxygen. Charge on oxygen is the number of electrons required to liberate 1 mole of oxygen. And remember, in electrolysis, for a monovalent element, any element in group 1 is monovalent. Sodium, potassium, lithium, even silver, that is a tangible metal that's not located in group 1. All of them are monovalent. So the charge on them is going to be 1. I don't need to put plus or minus there. How many Faradays that is required? That is what C represents for a divalent metal, like something like magnesium. What the charge on them? 2. So C is going to be 2. Magnesium, zinc, copper, lead, and so on and so forth. For a trivalent element like chromium, like aluminium, all right, like iron 3, then C is going to be 3. Forget about the plus that is there. Now, there are some gases. Look at hydrogen now. So hydrogen is an example of a diatomic monovalent element. For any element that hydrogen that is diatomic, diatomic means H2. Monovalent means H plus. If you want to write hydrogen ion, we write it as H plus. That's monovalent. If you want to write hydrogen gas, we write it as H2. That is diatomic. Other diatomic elements are things like oxygen, O2, nitrogen, N2, and so on and so forth. For any diatomic monovalent gas like hydrogen, the charge on them are always plus 2. They require 2 Faradays. For any diatomic divalent element like oxygen, diatomic O2, divalent, how do that? Oxygen ion O2 minus. The charge on them is minus 4, all right, which I've written down on this board before, the 2O2 minus. So meaning that the charge on them is going to be 4. So if you apply them here, number of mole of oxygen, that's the volume of oxygen, what we need, divided by the GMV, the gas molar volume, which is 22.4 Nm times the charge that particular oxygen requires, which is 4, the number of faradays required, then is equal to number of mole of copper. Copper is a metal, and number of mole of a metal is mass all over molar mass. The mass of copper deposited is already given as 0.635, and the molar mass of copper is 63.5 times the charge on copper. We all know that copper is a divalent element, that is 2. That's going to be 2 all over 1. So here, 4 times this, if I represent this volume by x for convenience, 4 times s gives us 4x all over, this is 22.4, is equal to, if you look at this times this divided by this. Someone very quickly, 0.635 times 2 divided by 3.5, 0.02. So we now have 0.02 everything all over 1. And then we cross multiply. 4x times 1 gives us 4x. This times this, that's 22.4 times 0.02. Don't forget in DMQ. And then we now have x now is equal to 2.4 times 0.02 divided by 4. What would this everything here give us? So that's it, 0.112 GMQ. So we are back to where we were before. So either we make this of the long method that we use, or we make this of the formula here. Once we do it right, the answer will be the same nonetheless. So that is for this. Let's come to number 8 now. Number 8 says a reaction is spontaneous under standard conditions if, and by the way, when you see the E naught, then it stands for the electrode potential of a cell that is under what we refer to as electrochemistry or electrolysis. Now, there are 2 types of reactions, either spontaneous reactions or non-spontaneous reactions. What are spontaneous reactions? Those are reactions that occur on their own without any external impetus. No catalyst needed, no heating needed, or any of such external factors. Doesn't need to be added. Look at your titration. If you prepare a certain amount of a base, you put in a conical flask and you add maybe 1 or 2 drops of indicator to it, and you put some acid in your bread. Once you open the tap and then the acid and the base come together and then you actually swirl them together, neutralization has occurred. It doesn't require heating or anything. That is a spontaneous reaction. So in chemistry, there are certain conditions for spontaneity of the chemical reaction. So for ordinary chemical reaction, not a redox reaction, for a reaction to be spontaneous, what we require is just the value of the Gibbs free constant. What about as delta G? When delta G is negative, it means the reaction is spontaneous. Because the value of G can be 3 things. G can be negative, G can be positive, G can be 0. So when G is negative, when delta G, the entropy, when the Gibbs free energy change is negative, it means the reaction is spontaneous. But this reaction here is combining 2 things together, not just the Gibbs free energy, but also the electrode potential. And it's opposite of each other. For a reaction to be spontaneous, the Gibbs free energy, delta G, must be negative, while the electrode potential must be positive. So all you have to do is look at the options. So that would be option, let's see, that would be option B, I think. Yes, option B. So that's option B. The standard electrode potential is positive, while delta G is negative. And just for you to be able to remember in a long time, there's an equation like that gives the relationship between the two of them that I can use to illustrate this to you. There is this reaction, delta G is equal to minus NF. This is the equation that connects the two of them. The Gibbs free energy change is equal to minus NFE. What does N represent? That's the number of electrons that is transferred during redox reaction. What does F? You know what F represents in electrolysis? That's the Faraday's constant, and 6,500 coulomb per meter per mole rather. And then E naught, that is the electrode potential. So we have already established the fact that whenever delta G is negative, the reaction will be spontaneous. Whenever delta G is positive, the reaction will not be spontaneous. It is also possible for delta G to be zero. What does it mean? The reaction is at the state of equilibrium. So these are the three possible scenarios that we have. Delta G being negative, that represents that the reaction is spontaneous. Delta G being positive, the reaction is non-spontaneous. And delta G being equal to zero, the reaction is at the state of equilibrium. But what do you think? Don't forget, F is only positive in 96,500. The only thing that can make this particular delta G here to be negative is if the value of delta of this particular electric potential here is positive. Because if this one, if the E here is negative, what do you think is going to happen to the particular minus? It cancels it and then everything becomes positive. So for a reaction to be spontaneous, delta G here must be negative and then the electric potential of the cell must be positive. So that's for this. Let's come to number 9. The Brown ring test for tri-oxygen ion is considered unreliable in the presence of which ion. Now we know what Brown ring test is. Brown ring test is used essentially in chemistry for determining or for telling for the presence of NO3 minus triosonitrate 5 ion. And why do we call it Brown ring test? Because when you carry out the test and it shows a positive result, there is going to be a Brown ring junction between the two layers of the substance. Don't forget, we first of all add that particular test substance that we want to test into the test tube, and after that, what do we do? Then we add what we refer to as iron 2 sulfate FeSO4. And then we now hold that particular test tube in a slanting position and then gently down the side we add concentrated H2SO4. If triosonidified ion is present, a brown ring color will be formed between the FeSO4 and also the H2SO4. So that is where the word brown ring comes in. But unfortunately, whenever there are presence of bromide and iodide ion, which are the answer by the way, whenever you have bromide ion and iodide ion, they actually make the test not to be reliable. Why is that? If we look at bromine, look at bromine. What's the color? Bromine water, reddish brown, which is going to actually interfere with it. So that even if there's no nitrate ion, even if it is bromine that is there, you will see that brown ring and you will think that it is nitrate ion that is present. So the reliability of brown ring test is actually affected by the presence of iodide ion, I minus, and bromine ion, Br minus. So that is option B. Let's go to number 10. Which part of a Bunsen burner flame is the hottest? Now, if I know about flame, we have two types, don't we? We have the luminous flame and then we have the non-luminous flame. Now, if this one is talking about the part, let's go back a bit. Okay, which part of a Bunsen burner flame is the hottest? So, like I was telling you, we have two types of flames. We have luminous flame and then we have the non-luminous flame. The non-luminous flame has 3 zones. Because at time they can ask you how many zones do this is equal to then times
Ṣé
the
náà ṣì wà lára
solution
ẹ̀?
C O P minus that's S and you know it's which over 1. So leave it there.
Got that system.
2 squared, that's 4. X squared, that's S squared, then times X. So 4x squared times X will give us 4S P. So that's how we calculate our solubility product. So that is option C. So that's for that. That's on number 13. Number 13 says precipitate or barium sulfate will form if the ionic product Q is so number 13 says a precipitate of barium sulfate will form if the ionic product Q is dash. Now, there are three relationships between ionic product Q and the solubility product KSP. These are the three relationships. When Q, that's the ionic product, is less than KSP, that is the solubility product, then it means the solution is unsaturated. What does it mean? When you say something is unsaturated, it means that it can dissolve more solid. After all, we say an unsaturated solution is a solution that can continue to dissolve more solute at a particular temperature. It is also possible that Q is exactly equal to KSP, meaning that the ionic product Q is equal to the solubility product K. Solution is now saturated solution. And when we say a solution is saturated, what does it mean? A saturated solution is a solution that contains as much solute as it can dissolve at a particular temperature in the presence of undissolved solute. In simple English, it means that that particular solution cannot dissolve any additional more solute. If you have maybe a cup of water and then you are adding sugar to it and you are selling it, it is salt. You add more sugar, you say it is salt. You add more sugar, you say it is salt. You are going to get a particular stage where additional sugar that you add only settles at the bottom, it doesn't dissolve anymore. That particular solution that now refuses to dissolve more solid is a saturated solution. But when you are still adding more sugar and the solution is still dissolving it, that is an unsaturated solution. But this is the third one. It's also possible that Q is now greater than KSP. When that happens, this is a super saturated solution. So when we say a super saturated solution, what does that mean? A super saturated solution is a solution that actually contains more solute than it can normally hold at a particular temperature. Talking about the English, what that means in plain English is a super saturated solution is any solution that when you add additional solute into it, the solute that has dissolved originally will come out. What is not coming out in chemistry is going to precipitate. Meaning that that particular solution is very, very unstable. Once you add more solute now, in the case of saturated, I told you, if you add more solute, that particular solute just go to the bottom and stay there. But in the case of supersaturated, when you add more solute, now what happens? It triggers. Even the solute that has dissolved originally, it becomes precipitated. So whenever the ionic product, which is the Q, is greater than the solubility product value, that's the KSP, the solubility product value or constant, then precipitation always occurs. Let's take a look at the question now. A precipitate of BaSO4 will form, which means that precipitation will occur if the ionic product Q is dashed. And from what I've written down on the board, you can see the only time that precipitation of a particular salt will occur is when the ionic product Q is greater than the solubility product constant, which is KSP. And if you look at the option, that is option C. I hope you know the word exceed means greater than. So that's for that. That's option C. Once again, if it is option A now, if Q is equal to KSP, it means the solution is a saturated solution. If it's option B, if Q is less than KSP, it means it's an unsaturated solution. It will dissolve more solid. But if Q is now exceeding means it's now more or higher than KSP, it means precipitate of what had dissolved originally will now become crystalline or precipitate and will come out of the solution, which is the correct answer here. And by the way, Q cannot be zero. It is either it is less than KSP, equal to KSP, or greater than KSP. It can't be zero. Let's come to number 13. In the R reaction, you can see the R reaction, X O4 minus plus H from H plus Ne to give this that particular arrows and that particular question mark is supposed to be an arrow pointing to the reactant and to the product side. Let's see the completion of the question. Let's see the rest of the question. Okay, so in the half reaction, you can see the half reaction. Then the question is asking us what is the value of n. This is the reaction SO4 minus plus 8H plus Ne minus to give us XO plus 4H2O. So this is what you do. Remember this 1 here, 1 times minus 1. That's minus 1. 8 times plus 1. That is plus 8. So if you add them together, minus 1 and this will give us plus 7. Then just ignore this for a moment. Let's come to the right hand side. This one is 1 times plus 2. This is plus 2. This one doesn't have any charge. But remember, when we are balancing our equation, we have to balance the charge as well. So there is plus 7 on the left hand side, there is plus 5, where is plus 2 rather on the right hand side. The question is asking us what will be the value of the electron here. That is, what must this particular n be? Don't forget, an electron is always negatively charged, meaning that negative of what number can be added to 7 in order to reduce it to plus 2. Everybody knows that. That's 5, which means that the correct answer here would be 5. Now, if it is 5, this 5 times minus 1, that's minus 5. When you add plus 7 and minus 5 together, you get plus 2. But if in an exam, for example, you don't need to go through all this round. Just focus on this and this. All right. Find the oxidation number of X here. Find the oxidation number of X here. Subtract them, and then you get your answer that you are looking for. So if you calculate the oxidation number of X here, X O4 minus. If I want to look at oxidation number of X here, I will now say this one is X. Oxygen is minus 2. There are 4 oxygen. That's minus 2 times 4 is equal to, what does this mean? Minus 1. Everything is equal to minus 1. Here, I will now have X minus, that's it, equal to minus 1. Then my X now is equal to minus 1. Minus 8 to the other side become plus 8. And then X is equal to plus 7. Take note of this. And then, let's come here. We're going to calculate here. The number of X here is already written on top of it. That's plus 2. What do? That's 7 plus 7 minus plus 2. That gives you 5. It's as simple as that. So just calculate the number of the element here, calculate the number of the element here, subtract then the electron that is required on both occasions. Either the one I explained earlier or the one that we just did here, the answer gives you 5. So that's for that one. Let's come to number 14. Which property increases down group 17? That's the halogen. I know some of you will be wondering that Do we have group 17? Don't we have only group 8 from 1 to 8? At times, they usually include the transition element. This is what I mean. Our periodic table, as we know it, is in this form. So this group 1, group 2, and don't forget, we usually have some elements between group 2 and group 3. We call the transition elements, and then we have our group 4, we have 5, we have 6, we have 7, and of course, we have our 8. So if you do it like this, it's going to be 8. This 1, 2, 3, 4, 5, 6, 7, 8. But at times, there are times that they don't just include this one. Don't forget there are elements in each of these. And if you know very good very well, there are usually 10 of 10. There are 10 elements, and there are 10 dimensional elements in each of the rows, from the scandium here to the same here. And then you also have 10 in the next one now, from the uteal all the way to your cardium, and then you also have another 10 in the last one, that is in the last third row from lung all the way to mercury. So 10, 10 in each of the rows. So meaning that you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. At times, the count is actually the rule according to the UPAC. It's only here in Nigeria that we usually ignore this. So when you are counting the elements here, it's going to give you 17. Let's do that together. This 1, 2, don't forget there are 10 here. So like a 1, 2, then plus 10 here. That gives us 12, 13, 14, 15, 16. 17. So that's it. So that's where the 17 that we are seeing come from. So it's either it is 7 good or it is 17. It means the same thing. So now back to the question now. So it now says which property increases down to 17? That is the halogen. Let's look at option A, electronegativity. We should know that electronegativity always what? Always decreases down the group. It doesn't increase down the group. As a matter of fact, electronegativity, ionization energy, electron affinity, the three of them, what do? They will decrease from top to bottom down the group, and they will increase from left to right across the period. The three of them, electronegativity will decrease down the group, electron affinity will decrease down the group, ionization energy will decrease down the group. So electronegativity cannot be the answer. The same thing, option B, oxidizing power. Oxidizing power, as a matter of fact, which one is, which element are the highest, which one is the most electronegative? Because the higher the electronegativity, the higher the oxidizing power. Which is the most electronegative element in the periodic table? Fluorine. And fluorine is at the very top of group 7, meaning that as we're going down, oxidizing power is actually decreasing, not increasing. So that isn't correct. Option C. Let's come to option D. Force ionization energy. I mentioned it just a few seconds ago that ionization energy, electron affinity, electronegativity, they all decrease down the group. The only thing on this board that will increase down the group for halogen is their boiling point. If you look at fluorine, that's F2. Underneath fluorine, you have chlorine, Cl2, bromine, iodine, and so on and so forth. And if you look at their boiling point, they gradually increase. As a matter of fact, we should know as good chemistry students that as we are going down the group of the halogen, the van der Waals forces are increasing. Isn't it? There's one thing that van der Waals forces depend on, and that is the molecular mass and the surface area. The higher the molecular mass, the higher the van der Waals forces, meaning that any element that has a lower molecular mass will have a weaker van der Waals force. And we know that the weaker the van der Waals force, the lower the boiling point. So if you look at the 4 elements in halogens, now there are 5 of them, and they also join the radioactive one, which is aspartame. If you look at fluorine, chlorine, bromine, and iodine, fluorine will have the lowest boiling point. Iodine will have the highest boiling point. Why? Because of their molecular mass. Because the higher the molecular mass, the stronger the van der Waals force. If you look at fluorine, the molecular mass of what's the atomic mass of fluorine is 19. That of chlorine is 35. That of bromine is 80. That of iodine is 135. So if you look at them, we see that fluorine has the lowest and iodine has the highest. So as the molecular mass is increasing, the boiling point is increasing. So the only property of this for the halogens that will increase as are going down the group is the boiling point. Once again, ionization energy will decrease down the group. Why does it decrease down the group? Due to increase in screening or shaping effect. These are other areas that JAMB do ask their questions from. They can ask you that in the periodic table, ionizing energy decreases from top to bottom due to that. The reason why ionizing energy decreases from top to bottom is due to increase in the screening or shading effect or due to increase in atomic radius. Don't forget, atomic radius will increase as I go from top to bottom. The same thing, electronegativity also decreases down the group. And anything like ionizing energy that will decrease down the group, automatically it's going to do the opposite across the period. It's going to increase from left to right across the period. Once again, they can ask you that on moving from left to right across the period, there is a general increase in the first ionization energy of element. This is due to that. The question is asking you, why is it that when you are moving from left to right across the period, there is an increase in ionization energy? It is because of increase in nuclear charge. All right. The reason why ionizing energy increase across the period is due to increase in nuclear charge. Whereas the reason why ionizing energy decreases down the group is due to either increase in atomic radius or increase in screening effect. The same thing with electron affinity. Electron affinity is defined as the energy or the heat that is evolved when an electron is added to a gaseous neutral atom to form a gaseous negative ion. Also, when you are going down the group, electron affinity also decreases. And if you are moving across the period, electron affinity also increases. And the same reason why ionizing energy increases across the period due to increase in nuclear charge. That's the same reason why electronegativity increases due to increase in nuclear charge. That's the same reason why electron affinity increases across the period. That is increase in nuclear charge. But take note that there are usually two major things that increase down the group. Now, I've given you three things that increase down the group. Electronegativity, it decreases down the group. Ionization energy, it decreases down the group. Electron affinity, it decreases down the group. But there are two major things that increase from top to bottom down the group. Number one is atomic radius. When you are going down the group, atomic radius increases, meaning that look at group one. Lithium is at the top. That's if I'm ignoring hydrogen. Lithium is at the top. It will have the smallest atomic radius. Sodium, which is below it, will have a higher atomic radius. Whereas cesium, which is second to the last, is going to have large atomic radius. So as I go down the group, atomic radius is increasing. Another thing that is increasing down the group is electropositivity. What electropositivity? The tendency of an element to lose electron. That's electro is the opposite of electronegativity. Okay, so the tendency of an element to lose electron is electropositivity, and as I go down the group, it is also increasing. Another one is metallic properties. As I go down the group, metallic property is also increasing. That is why if you are given four metal like lithium, sodium, potassium, and rubidium, and they're asking you which one of them is most electropositive, electropositive are at the very bottom. The one at the very bottom, that is the one that's going to be most electropositive. And which one of them is going to have the higher metallic property is also the same. The one that's at the bottom. Lithium is at the top. It's going to have the lower, it's going to have the lowest electropositivity. And it's going to have the weakest metallic property. And rubidium, which is below, For example, it's going to have a higher electropositivity and a higher metallic property. So that is for that. Let's come to number 15. Electrovalency is most favored between. Now, what is electrovalency? Electrovalency is also referred to the ability of an element to form ionic bond. Even take a look at the word electrovalency. What's another name for ionic bond? Electrovalent bond. Okay, so when we say electrovalency, it's talking about the tendency of an atom to form ionic or electrovalent bond. And there are two conditions. There are two factors that favor electrovalency. Number one is low ionization energy of the metal, and number two is high electron affinity of the non-metal. Once again, the two factors that favor electrovalency are number one, low ionization energy of the metal, and number two, high electron affinity of the non-metal. And if you look at the options, then we'll see that's going to be option C, elements with low ionization energy, that's the metal, and high electron affinity, that is the non-metal. So that's for this. And if I want to change it, I'm changing the electrovalency to covalency. What covalency now? That's the tendency of an atom to form a covalent bond. What then will be the two characteristics? What will be the two factors that will encourage the formation of a covalent bond? All you have to do is just change the low in the ionization energy here to high. Both of them will be high, high. That's high ionization energy of the metal or the element, and then high electron affinity of the element. Both of them for two. Okay, so number 16 is asking us how many lone pairs and bonding pairs are in a water molecule. Now, water molecule, under shape of molecule is V shape or bent, or we call it angular. Water molecule always have a V shape or a bent shape or an angular shape. And we are asked what number of lone pair and bonding pair electron do they have? They have two each. Two lone pair electron and two bonding pair electron. You can use the formula I gave you earlier on to calculate the number of lone pair electron. If you still remember, the formula was V minus B all over 2. And we're talking about water molecule, which is H2O. The central atom is oxygen. It's like this. The shape of water molecule is V shape. And oxygen is at the center. And we know oxygen has atomic number of 8. Meaning it's going to have 6 valence electrons. So the number of valence electrons is 6. That's 6 minus how many bonds does it form? This 1, this 2. That's minus 2 all over 2. So they become 4 all over 2. So it means it's having 2 lone pair electrons. How many bond pair electrons? You can see the number of bonds. That's the number of bond pair electrons. So this one bond pair, this one bond pair. So the number of bonds, that's the meaning of bond pair electrons. If it is 3 bonds here, that's going to be 3 bond pair electrons. If it's 4 bonds, that's 4 bond pair electrons. It's as simple as that. So we know now that it has 2 lone pair electron and then 2 bond pair electron. And another thing we should know is they can also ask you for the bonding angle of a water molecule. The bonding angle of a water molecule is 104.5 degrees. Once again, the bonding angle of water molecule is 104.5 degrees. Although I've noticed in some jam questions, they usually approximate, they give the answer to the nearest whole number. So you might not see 104.5 there. What you might rather see instead is 105 degree. The exact value is 104.5 degrees, but you could as well see 105 degrees. So, and not only that, the hybridization of water molecule is sp3. So we have known it is now. The bonding angle 104.5, the hybridization sp3 to also water molecule is V shape or angular shape, or we can call it the bent shape. So that's for this. Let's come to number 17. A dated bond. Let me know when it's written. Okay, so let's come to number one. Is in which of these covalent found for bond. If you look at methane, methane also only form the normal covalent bond. It doesn't form dative bond. If you look at magnesium chloride, even magnesium is a metal, chlorine is a non-metal, so that is ionic or electrovalent bond. I've told you today examples of compound that have dative bond. And the correct answer here is option B, hydrozonium ion. Once again, for dative bond, you have ammonium ion, NH4. Maybe I can give you like 6 compounds that possesses dative bond. You can make this one as your number one. If you don't know that already, hydrogenium ion, H2O plus, that's dative bond. Number two, ammonium ion, NH4 plus. It also has dative bond. That's two now. The first one is H3O plus. The second one is NH4 plus. The third one, NH4Cl. That's ammonium chloride, NH4Cl, ammonium chloride. The next one is ozone. We've done it today as well. Ozone O3, it also has dative bond. The fourth one, carbon 2 oxide, that's CO. The one we call carbon monoxide, it also has dative bond. That's another example. Another one is boron. So we want to understand it. Boron, trifluoride, ammonium, hydrogen, that is B, H3. When you see the dot here is an adduct. So boron, trifluoride, ammonium adduct. Adduct is spelled as ADDUCT. So the type of bond formed between boron trifluoride and ammonia is also a dative bond. And last but not the least, aluminium chloride dimer. Aluminium chloride dimer, aluminium chloride dimer. That's the formula. Al2ClC. That's aluminium chloride dimer. Even from the word dimer, it means two. So this aluminum chloride, AlCl3. And dimer means 2 moles of that. So Al2 and then 2 times 3, 6. So aluminium chloride dimer. So these are examples of compounds that exhibit or possesses dative bond. And remember, before any compound, before any substance can undergo dative bond, it must, number one, be, one of them must be a Lewis base. What's a Lewis base? A Lewis base is a substance that possesses lone pair electron. So it must be able to donate lone pair electron to another substance. So that is why it is just like ammonia. Ammonia is a Lewis base, all right? But ammonia on its own does not possess dative bond. But when ammonia combines with hydrogen ion, for example, NH3 plus H plus to give us NH4 plus, now that is a dative bond because the ammonia will possess one lone pair electron. It should now donate the lone pair electron to the hydrogen ion, which does not have any electron at all, so that the hydrogen ion will also be able to have that particular complete or a duplet octet structure. So the answer to number 17 is option B. Let's go to number 18. Van der Waals forces increase in strength with dye. We mentioned it today while we were talking about I think yeah, we were talking about, I don't know which number, the number of the question, we are talking about which of the following increases in talking about group 17 element, and we chose boiling point then. And I was telling you that whenever the molar mass of a particular element increases, that also increases the Van der Waals forces, and that is the clue to answering this question here. So Van der Waals forces increases with increase in molecular mass, and also it depends on the shape of that particular molecule, which is the surface area here. So van der Waals forces increase in strength with increase in molecular mass and surface area. The higher the molecular mass, the stronger the van der Waals forces. The larger the surface area, the larger the van der Waals forces. And don't forget, van der Waals forces, they are not actually born. They are intermolecular forces of attraction. And out of the various intermolecular forces of attraction that we have, van der Waals forces are the weakest of them. Van der Waals forces are weaker than dipole to dipole attraction. Van der Waals forces are weaker than even hydrogen bond. And that is why majority of certain gases that have very low boiling point possess van der Waals forces. There are questions that can be asked of you. Why do gases such as nitrogen and oxygen, why do they have very low boiling point? Is it because of weak van der Waals forces? Look at a gas like hydrogen with a boiling point of about minus 152 degrees Celsius. Very, very low. And the reason for that is van der Waals forces. Look at gases like oxygen and nitrogen with boiling point like minus 196 degrees Celsius and minus 183 degrees Celsius. The reason why it is that low is because of weak van der Waals forces. Not only that, look at some elements like sublimate, elements like dry ice, that is solid CO2. A sublimate changes directly from the solid state to the gaseous state. Why? Because of weak van der Waals forces. What about elements like iodine that also sublimate? Elements that usually sublimate usually possess this van der Waals forces. Not only that, look at graphite. One of the use of graphite is as a dry lubricant. Why is graphite a very good dry lubricant? Because the layer can easily slide over one another. And why are the layers? Why are the layers why are they easily sliding over one another? Is because of the weak van der Waals forces holding the layers together. So these are the things you need to know about van der Waals force. And by the way, van der Waals forces are also called London dispersion forces. Once again, van der Waals forces are also called London dispersion forces. So let's come to number 19. Stop at number 20 and then. Okay, so number 19 now. A molecule with a net dipole moment of 0 is dash. When you see a question like this, all you need to do is ask yourself, does it have linear molecule? If the answer is yes, pick that and go your way. All linear molecules have net dipole moment of 0. And if you look at the option, there is a molecule with linear molecule there, with linear shape there. CO2 is a molecule with linear shape. This CO2. All right, so CO2, as a matter of fact, is very common in Jan. It's one of the few examples that are used. Carbon dioxide is a linear molecule, you can see there. An linear molecule, the bonding angle is what? 180 degrees, and the hybridization is what? SP. Once again, for any linear molecule like CO2, carbon dioxide, the bonding angle is 180 degrees, and the hybridization is SP. Apart from CO2, other linear molecule are things like ethane. Ethane is also a linear molecule. This is the shape of ethane. You can see the bonding angle is still 180 degrees. That's angle on the side. The bonding angle here is 180 degrees. Not only that, you also have beryllium chloride. Beryllium chloride, BeCl2, is linear molecule. B is at the center, this is chlorine. This is chlorine. The bonding angle is 180 degrees. Mercury 2 Cl2. If I have HgCl2, all I have to do is replace this one with Hg. So you can see. So another example is carbon 4 sulfide CS2. And CS2 is carbon air, this one sulfur, and this is another sulfur. So I think I'll give you not less than 5 examples. CO2 is a linear molecule. Ethane C2H2 is a linear molecule. Beryllium chloride BeCl2 is a linear molecule. Mercury 2 chloride AgCl2 is a linear molecule. Carbon 4 sulfide CS2 is also a linear molecule. All linear molecules, they have net dipole moment of 0. Not only that, they have hybridization that they have bonding angle of 180 degrees. And then we take the last one.
Must probably 20 then. My phone 15. Sorry.
Hello. With the look of it, we can't run biology today again. All you guys are ready to stay till 9 p.m. Oh, we should just take it till tomorrow. See? Are you ready? Till tomorrow. You go day after tomorrow. Alright, we'll be running the physics questions after now. Are you getting it? Physics after now. But you guys, some of you are tired. Have you? Give me 15 minutes break. Or no break at all. If you want 15-minute break, let me see you 15-minute break. Okay. No break at all. Physics straight. Alright. So we'll be giving you 15 minutes after this last question. Hello, hold on. 15 minutes, but 15 minutes should be 15 minutes. We told you 30 minutes break the other time. I saw somebody at Benoni, Adebayo. You understand? Okay. Coming back after 1 hour. So 15 minutes will be 15 minutes. So once it's 10 minutes to 4, we start with physics. And we'll stop by 6 sharp. Because I know some of you actually came from a far distance. So we are stopping by 6 today. So after this last question, we give you break for just 15 minutes. So either you are here or not, we are starting with physics straight. Alright. So tomorrow, please, tomorrow, let your 7 a.m. be 7 a.m. Let your 7 a.m. be 7 a.m. Because we are starting biology.
Already 7:30, right?
And I come first on I can see 7 married in 7 days, so that I take only 3 hours.
Alright, hello. Tomorrow, 7 a.m. Biology slash mathematics. 3 hours straight, 7 to 10. Biology slash mathematics, 7. No going back. Are you getting it? So we are releasing you 6 sharp today. So tomorrow, biology slash mathematics. Then after that, you do physics. Okay? Then we know what to do about chemistry if we don't have the chance. So biology tomorrow, 7 a.m. to
And so let's look at number 20. It says, what is the shape of a molecule with 2 bonding pairs and 2 lone pair electrons? We have done it before. Think of a molecule with 2 bonding pair electrons and exactly water. And we have said that water has a V shape or a bent shape or an angular shape. If it is ammonia, what is the shape of ammonia? Trigonal pyramid. For ammonia, trigonal pyramid, that's the shape. If it is something like ozone, the shape of ozone is even as the shape of water. It's also V shape. If it's carbon dioxide, it is linear shape. If it is methane, methane CH4 tetrahedral. What if it is boron trifluoride BF3 trigonal planar? Anything like this. BF3 B, Cl3, B, B, R3, Al, H3, Al, Cl3. So far, this is what we need to focus on, nothing more. If the number of the elements attached to them are 3 in number, and all the elements here are in group 3, it will always be trigonal planar. Boron is a group 3. And this one is 3 molecules. You don't need to bother yourself. That's trigonal planar. Aluminium is in group 3. You have 3 chlorine atoms attached to it. Now, if it is now Al, H4, it can no longer be trigonal planar. It will now be tetrahedral. But if the elements here are all elements in group 3, and there are 3 elements attached to them, that is trigonal planar. And lastly, any trigonal planar molecule, I'm talking about all alkanes are trigonal planar. Alkanes like ethene, propane, butane, any hydrocarbon that end with ENA is having trigonal planar molecule. And any molecule with trigonal planar, the bonding angle will be 120 degrees. Once again, I told you the other time, the bonding angle for linear molecule is 180 degrees. The abbreviation is SP. But for trigonal planar, the bonding angle is 120 degrees and the abbreviation is SP2. Once again, the bonding angle for trigonal planar 120 degrees and the abbreviation is SP2. So you go for your break, then come back by 15 minutes time, then we look at physics.